Okay, this will be the polynomial unit, little review problems. So let's take a look at some of these here. So problem number one, we want to find the properties of some given equation here. So they give us f of x equals negative x to the fourth plus 3x squared plus x. And we need zeros, we need maximum and minimums. Okay, so why don't we take a look at the graph on the calculator. And let's see, I already have some of these in here. So that first one is a different problem. And then so I'm actually just gonna unhighlight the two I don't want to see just because I'm gonna use them later. But we would just enter the one we want, okay, which is, it's in Y2 right now. And if you haven't seen that with the calculators, you can just unhighlight the equal sign and it won't graph all of them, but this way we can at least have other problems in there from other times. So that one in Y2 is the one we're looking for. So let's go ahead and check that out, see what it looks like. And here it comes. Okay, so it looks like it was a fourth degree with a negative leading coefficient, so we can see about the end behavior. This one's going to have both ends going down. Okay, so I know those would continue downward. And it looks like we have it looks like just one real zero there, right? Now, let's think about what's going on. I'm sorry, two. What am I talking about? There's two zeros. So there's a zero here and another zero here. Okay, so let's find those. So just a quick recap, you can go into second trace and find a zero. And that's close to one of them right there. So left bound, I'm just going to go a little bit to the left of it just to be safe, make sure that I wasn't right at the zero. Press enter to give it a boundary. Now it's asking for a right bound, so you just scroll a little bit to the right here. So something like that would be fine. For the guess, I'm just going to go ahead and get kind of close to it and press enter one more time. And there's one of the zeros. Okay, there's a zero right at zero. Okay, and the other one now, just to find that one. Again, we go back into that same menu, find the zeros. Now this time when you do the left bound, you need to be a little bit above the zero. Okay, so what I'm really looking for a left bound, I want to have a left boundary where the y value is some positive number at that point. And my right bound, I need to make sure the y switches to negative. Okay, so that I know the zero will be in between a positive y value and a negative y value. And then just get kind of close for the guess again, press enter one more time. Here's our actual zero, x equals 2.1. Now if you get something like this, okay, just got to remember that e negative 12 really means you're taking the 1.5 times 10 to the negative 12. In scientific notation, 10 to the negative 12th is a really, really, really small number. So this is essentially equals zero, the y value there. And the weird thing is you could do this, I could do this problem 5 minutes from now and it would give me a different, it might not be 1.5 anymore, but it would be e negative something. And you just have to recognize that that's zero. Just based on the calculator, the way it does things numerically, approximation, so sometimes it doesn't say exactly zero. Okay, so that would be the two zeros. And just to find the min and max, just to review that really quick, there looks like a maximum up here. So we could find that similarly, just going into that same screen, second calculate. 4 is the maximum here. And we'll just give it boundaries too, just so the calculator knows where to look. So go to the left of it a little bit, so that would be safe. We'll go to the right a little bit. And then enter one more time, and it's going to go ahead and give you the maximum. So that's the coordinates of the maximum. Now this one doesn't have a minimum. If we kind of follow, this thing's increasing, 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 and then right here when it starts to change, it decreases now. That's going to be the only extrema. So that's the maximum there. So the answer to this one was B. Okay. It had two real zeros. The coordinates were given there, and the maximum and minimum match up as well. Okay, moving on to number 2. It was actually the exact same type of problem, so I'm not going to go through all the details on it, but the answer to this one you should see would be B as well. Okay, if we were to graph that one, you would find it had 3 real zeros, it had a maximum and a minimum, and then we could find the coordinates for each zero. Okay, number 3, completely factoring. So this one, to me, it looks like, with having 4 terms there, it looks like a grouping problem. So that would be my first thing to try. I would actually look through and see, is there any common factor in all of the terms? And if there's not, then we might try other methods. Okay, so let's look at the grouping method again. Since we didn't see any common factor, there is no common factor. So a lot of times what I found works is if you were to group it in the first two terms and the second two terms and try and treat them as their own little problems. So for example, the first one, if we were to do some factoring of the yellow stuff, I see they share an x squared, goes into both of them. And the leftover factor would have to be x plus 5. Right? If you distribute that, that would get you the x to the third plus 5x squared back. Okay, and then the other terms, the blue stuff, they don't really look like they have anything, but you always have the option of pulling a 1 out. Right, so bringing a 1 out in front, I would still need an x to multiply to be x, and I would still need a plus 5 to distribute to become the 5. Okay, so this is kind of where we're at now. Still an equal 0 on there. And then we want to go ahead and keep factoring. So now the thought is they actually do share a common factor now. The yellow stuff has an x plus 5 factor, and so does the blue stuff, right? So we are able to bring that out front as a common factor, the x plus 5. So that kind of got brought out front from both. And then the leftover stuff now is just the x squared and the plus 1. Okay, and that would be complete. That would be factorable. So just be careful. The x squared plus 1, this term right here is not factorable anymore. If it were x squared minus 1, if it were the difference of the two perfect squares, then we could break that down a little farther. But this one should be a. Okay, moving along, number 4, another completely factoring type of problem. So this one again, we kind of look for common factor. And this is kind of a weird one, only two terms, there's really no common factor, but this one does follow the steps or the format of something cubed plus, if you think about 64, that is really 4 cubed. Okay, so there's a rule for that, and this is just one of the formulas you kind of need to remember. The way we talked about it was a cubed plus b cubed always equals a plus b times a squared minus ab plus b squared. Okay, so it's always, if we talk about the signs, remember it's always the same sign as what you have here, then the opposite, and then always positive. So remember that SOAP, same opposite, always positive. So for instance, if this was actually a minus, then this one would be a minus to be the same. This would have to be the opposite, and this one would stay as a plus. Okay, so that's the two formulas, and this problem fits that. So we can go ahead and factor it out. This is really like our A and our B. Okay. Right, A is x and B is 4. So if we just plug in, it's going to equal, setting it up over here, A plus B. So for our problem, it's x plus 4. Okay, A squared, remember our first term is x, so x squared minus x times 4, we write that as 4x, and then plus B squared, so plus 4 squared, which is 16. Okay, and then we can just go ahead and stop there, okay, because the quadratic factor here, again, not factorable. There are no factors of 16 that add up to negative 4. Okay, so that would be completely factored. Now, if you had to solve it, if we had to finish this, you would use quadratic formula on that factor I underlined, and you could get answers of x equals negative 4 from this one, and then whatever these two give you from the quadratic formula. But we didn't have to solve this one. We just wanted to factor it. Okay, number 5, finding all zeros of a polynomial. So again, there's a few ways to do this. You could throw in your calculator and graph it, um, and that'd be totally fine. It'd probably be easier than what I'm about to do. But I'm just going to show again how this is tied to factoring still, because this one I notice is factorable. It's a lot like the one we did a couple problems ago as with the grouping problem. So I notice in the first two, again, these two share an x squared. I'd be left with a 3x plus 1. Right, and then the next ones, again, it doesn't look like anything, but they do share a 1 at least. So I can bring out the minus sign and then a factor of 1. And it would have to be 3x plus 1. Okay, because again, think about that this negative right here would distribute to be minus 3x, and it would distribute to be minus 1 like they were up here. So that's the correct factoring. Then we can go ahead and finish the grouping. They share a 3x plus 1 now. Common factor, bring it out front. Leftover stuff is x squared minus 1. Now here's one where it is still factorable. Okay, the 3x plus 1, but this right here is the difference of perfect squares. Right, x plus 1 and x minus 1. All right, and that would be the final step to factoring it, but this is finding all zeros. We're basically finding when this stuff all equals 0. So if we were to just set each factor equal to 0 and solve, if we set 3x plus 1 equal to 0, when we subtract the 1 and divide by 3, we would get x equals negative 1/3. Okay, this one setting equal to 0 would get you x equals negative 1. And this one would solve to get you x equals positive 1. Okay, so it looks like D would be the answer for this one. And again, this one, finding all zeros, feel free to graph it. Sometimes the graph shows them all. Ones that are factorable, the graph would also show them. But yeah, that's solving it. Okay, number 6, what type of model would be best for this? Okay, so it looks like we're kind of increasing, hit a peak, decrease, kind of come back up. And I don't know if it goes back down or back up. I'm not sure. But what I do know is this thing shows 2 turning points for sure. Okay, so there's no way it could be a quadratic or linear. Okay, it just can't. Quadratics would only have 1 turning point. Linears don't have any turning points. So cubic would be the way to go here. Now, if we know it decreased again, then we'd have to go higher degree than cubic. But from what we see, who knows? We're not sure. So I would probably go with cubic for this one, but definitely not quadratic or linear. Okay, number 7, straight division problem. This one is nice because we are just dividing by a binomial. Okay, the thing we're dividing by is just a binomial. It's a linear binomial, right? There's no exponents in there. So we can do straight synthetic division for this one. So since we're dividing by r minus 5, we actually want to use a positive 5. And I'm going to set up my coefficients, and we will do the division. Okay, so coefficients from the thing we're dividing by are just a positive 1 r cubed, positive 2 r squared, negative 38r, and then a 5. Okay. Now I was being careful, making sure that we didn't skip anything. Make sure you have third power, second power, first power. Okay. If we had any missing, we'd have to use zeros in their place, so just be careful there. And then the synthetic process is bring down the first term, and that 1 is going to get multiplied by the 5 that's in the box there, so 1 times 5. And then we're going to add straight down. So this is different than long division where you subtract. Synthetic, you add. So 2 plus 5 is 7. 7 gets multiplied by the 5. Okay, and that is going to, when we add those, become a negative 3 still. Right, negative 3 times the 5 is negative 15. And our remainder here will actually be a negative 10. Okay, so it looks to me like we have coefficients of 1, 7, and negative 3, remainder of negative 10. And we need to think about now, if we started with a third degree term and we divided it by a first degree term, our answer, when you subtract those exponents, will need to be second degree. So this is now a coefficient on r squared. It was a positive 7r to the first, a minus 3. And then with our remainder, so we would write it this way, r squared plus 7r minus 3. And we always do the remainder goes over the thing we divided by, which in this case was r minus 5. Okay, so that would be our answer there. So it looks like B for this one. Okay, number 8, good old-fashioned quadratic formula problem. And you can try factoring if you wanted to. If you wanted to multiply the factors, multiply 6 times 2, multiply the 8 times c to be 12, and then try and split the 5 up. And it may or may not work. I'm just going to jump right to quadratic formula because I know that always works. So let's get it set up. So we know x is going to be the opposite of b, so negative 5, right, plus or minus. Square root of b squared, so 5 squared is 25. I like to do that step before I even write it down. Minus 4 times a times c, right, all over 2a. Okay, so let's do some simplifying here and see what we get. Looks like negative 5 plus or minus square root of, I know it's 25 minus, what would that be, minus 48? 4 times 6 times 2, yep, so 25 minus 48 all over 12. Okay, so we'll keep simplifying. Negative 5 plus or minus the square root of 25 minus 48 should be negative 23 all over 12. And then we do want to simplify a little bit. I definitely don't want to leave a square root in the, or negative under the square root, right? So off to the side here, if we think about the square root of negative 23 is really the square root of negative 1 times 20, square root of 23. Okay, we know this guy is what we call I. That was what was defined to be I. Now 23, can that be broken down? Are there any perfect squares that go into it? I don't think so. Okay, so it looks like we're kind of stuck, but negative 5 plus or minus I root 23 all over 12. Okay, so we didn't have to break down the 23 because there was nothing to break it down with. Okay, so here are the two answers. You can see they just kind of split up. Here's the plus and the minus that we had right here. Okay. Alrighty, number 9. Let's say we're trying to find all the zeros of a cubic polynomial. We graph the function and find that there's only one real zero. So something like there's really one zero here, and let's just say for the sake of example that's the only zero, so maybe it does something like this or whatever. Who knows what it does, but it only has one real zero. We know since it's a cubic it should have 3 total zeros. Okay, so there are some other ones out there, and if they're not showing up on the graph they have to be imaginary. Okay, so what would we do to find those? Okay, so here's the thought. We know x equals 3 is a 0, right? So that tells me that there's a factor, right? The polynomial equals x minus 3 times some other factor, right? And I knew x minus 3 because if think about it, if you solved that, set that equal to 0, that would get you this answer as a 0, right? So when you know a 0, you actually know a factor as well. And now to find the other factor, what we would have to do is take the original f of x, the original cubic function, and we would have to divide it by x minus 3. And then we would end up with the quadratic that we could then solve. So for this one, we should actually be dividing by x minus 3 and then solve the quadratic. Okay, and then this was one extra problem. We didn't see this one in the trail in class, but I wanted to make sure we walked through one like this. So let's find all the zeros exactly. Let's see what we got going on. Okay, so let's should we get a list of possible zeros just to follow all the steps? So list of possible rational zeros. Okay, because just by looking at the thing, I don't think it's factorable. Even grouping, if I'm looking at that 38 and that 33, that's really not going to do much for us. So the possible rational zeros, just to give us a starting point, I need factors of 33. So plus or minus 1, plus or minus 3, plus or minus 11, and then factors of the leading coefficient is just 1. Okay, so if there's going to be a rational zero, it's going to be one of these numbers. Okay, so let's take a look. Let's graph it and see if any of those work. So then we will be able to divide something out of it. Okay, so let's go into the calculator and let's graph. Okay, and here's the graph of this thing. So it looks to me like I can see three real zeros. This one looks like it may be rational. It looks like it might be at -3. So that was in our list. So let's try -3. I'm going to go to trace. And I'm just going to type in now -3 just to make sure. And it worked. Okay, you could have also gone to the table, but the nice thing about the trace is if you wanted to try fractions, you can try fractions, and your table is normally set up to only show whole numbers. But we got 1, 0. Okay, and it looks like these other two, I don't know if they would be in our list. Remember, our list actually only had whole numbers, didn't it? So our list was either plus or minus 1, plus or minus 3, plus or minus 11. So what that tells me about these other ones Oops, wrong. These other ones are actually going to be irrational. Okay, and if we need them exact, I can't just write them as a irrational decimal from what the calculator shows. Like we did with number 1 and 2, we just did the left bound, right bound stuff. I can't do that. I need these exact. But I know I have a 0 at x equals -3. Okay, that tells me that I have a factor of x plus 3. So we can divide that polynomial by x plus 3, and then we can finish the problem and get exact answers. Okay, so let's do that. So the original polynomial, we are going to actually divide by x plus 3. Okay, and let's do that synthetically. So I'm going to use, remember the 0 that we actually found was -3, so that's what we use with synthetic division. I have coefficients of 1, 12, 38, 33. Okay, if we do the synthetic, bring the 1 down, multiply by -3, add those to be 9, -27, add those to be 11, -33, and we should definitely get a 0 here as a remainder, right? We knew that -3 was a 0, so that worked. Now all we have to do is take this answer, which is a quadratic, and we have to solve it using the formula. Okay, so if we do the quadratic formula, opposite of b, plus or minus square root of b squared minus 4 times a times c all over 2a. All right, and we'll do some simplifying. Looks like -9 plus or minus square root of 81 minus 44. Okay, so 81 minus 44, 37. Am I? Yep, okay. Sorry, it's early. All over 2. Okay, so that looks like our answer, -9 plus or minus root 37 all over 2, and then the first one we had gotten was -3. So it looks like D should be the answer. Let's just make sure it's right. Okay, we can check these. I'm telling you, these are the two that the original graph showed. So let's try -9 plus root 37 all over 2. Let's just go into the trace here. Trace. And I'm going to do -9. Oh, let's put parentheses around here. -9 plus root 37. And I want that whole thing over 2, right? And this is just going to verify. Okay, that's the one that's showing up right here. Okay, that's the decimal approximation that we didn't want. We wanted it to be exact. Okay, and the other one should be the opposite, -9 minus root 37. All that divided by 2. And that should get me this one right here. Okay, let's just make sure it does. Yep, there it is. Okay, so that's kind of a way to verify it. And again, the only way to get them exact is through quadratic formula. So exact is with a square root in there, not just a decimal approximation. All right.